Io is the most volcanically active body in our solar system. But what's it made of? In this video, I'm going to be talking about just that, both on the interior of Io, on the exterior of Io, how we know what we know, how we get that data, how we extrapolate what's on the interior of Io, and what we still don't know, and how we might go about getting more information in the future. So for a little bit of background about Io, I won't go too in depth because I do have another Io video where I talk about Io in general and its volcanism in general, and you can check that out. I'll link it to the top right here. But basically, Io is one of the 4 largest moons of Jupiter called the Galilean moons or Galilean satellites. These include Io, which is closest to Jupiter, and then Europa, Ganymede, and Callisto. And Europa, Ganymede, and Callisto are icy satellites, or icy moons. They're covered in ice, and some of them have water oceans, liquid water oceans, possibly, likely. And those are really exciting for the prospect of life. But Io is not, it doesn't have an ocean. It doesn't have an ice shell. It's way too hot for that. And it's actually really, really volcanically active. And yes, it doesn't have the prospect of life, but it is super interesting in many other ways. First of all, there are only 2 volcanically active bodies in our solar system currently, and these are Earth and Io. And Io is even more volcanically active than Earth. And how is this body in the outer solar system orbiting Jupiter so far away from the sun hot enough to support volcanic activity, you ask? Well, it's all having to do with tidal heating rather than solar heating. Tidal heating is a phenomenon I talk about in the first Io video, but the gist of it is that it's stretched and pulled in ways by Jupiter, since Jupiter is so massive, as well as these other moons. And because of this stretch and pull on Io constantly, it's got a lot of heat and energy, and that causes it to be super volcanically active. But we still don't understand fully how tidal heating works, how tidal heat is dissipated through tidally heated bodies. We're still working on that, and you'll see that throughout this video. But to get to the topic of today's video, we're talking about Io's composition. And it's really interesting because there's still a lot of questions and hypotheses around Io's composition, especially its lava composition at the surface, which can tell us a lot about its interior composition, where that lava is sourced, where it's coming from. So Io has both silicate and sulfur volcanism, or lava, on its surface, and that's because it's just intrinsically really rich in sulfur, and so it has all these different sulfur compounds that also contribute to all the different colors of Io. So you can see Io in this picture to the right with yellows, greens, red, orangish colors. All of these are sulfur-rich compounds. The whites that are either, volatiles within the silicate lavas, and silicate lavas are just like the dark black basaltic type things like we have on Earth. And then there's sulfur lava flows on Io. There's kind of white sulfur dioxide condensation frosts on Io, and also yellow parts that are the condensed frost. So there's all this different sulfur stuff on Io that is just, it makes it very different than Earth, but it's similar to Earth in that it does still have silicate volcanism. So silicate material, just like we have on Earth, erupts and forms lava at the surface as well. But what we still don't know about this silicate lava is what composition of silicate is it? So, for example, on Earth, we have felsic to mafic silicate lavas, such as rhyolitic or granitic composition, that's the felsic side of things, versus basaltic and even more toward the ultramafic side of things like peridotite. We have all of these lavas on Earth, but on Io, we're not sure the relative contribution of felsic to mafic lavas, or if there's any felsic lavas on Io, because observations seem to show that it's very low viscosity and mafic lava. Now, don't worry if you don't know what any of these terms mean, like viscosity, mafic, felsic. I'm going to talk about this in just one second. But why this is important is because the silicate lavas at Io's surface can tell us a lot about the interior of Io, the mantle, where that lava is coming from, the mantle's composition, the mantle's differentiation state. I'm going to define that later as well. And also the history of Io, when it formed, how it formed, what it formed with in terms of constituents, and can tell us a lot of these things and how Io has evolved through time, both its interior and exterior. And like I mentioned, observations of Io have indicated low viscosity and high temperature silicate lava at Io's surface. But what does this mean? So let me talk a little bit about magma viscosity before we get back to Io here. So viscosity just means resistance to flow. So for example, honey is more resistant to flow than water. So honey is more viscous than water is. Water is more flowy, so it's got a low viscosity. And low viscosity magma tends to erupt in less violent eruptions on Earth than high viscosity magma. And that's because it can allow volatiles or gases to escape more easily. And just imagine blowing bubbles into water versus blowing bubbles into honey. It would be a lot harder for those gases or volatiles to escape the honey or the viscous magma, and that causes an increase in volume and therefore a very explosive eruption. Now, if you watched my igneous petrology playlist, you probably recognize this slide, and it's because it's an exact copy of what I talked about in that video. So if you want to go see more about this, you can check out my silicate lavas video in my igneous petrology playlist. I'll link it up here to the top right if you want to check it out. The other thing I talk about in that video is what controls magma viscosity, and that is two main things: temperature and composition. So if you remember, we said Io has a lot of low viscosity and high temperature lava, and that's because they have an inverse relationship. Increased temperature typically decreases viscosity. But composition is really the main control on viscosity of magmas or lavas, and this is because of silica polymers. The more polymerized or long silica chains are present within the magma, the more viscous that magma will be. Whereas when the silica polymers are not as long, it's not as highly polymerized, and they're broken up by network modifying ions, those magmas have a lower viscosity. And these are typically things like basaltic lavas on Earth, whereas the high silica-rich, very polymerized lavas are things like rhyolitic lava or granitic magma on Earth. And it basically means that these rhyolitic lavas will have very explosive eruptions, and the basaltic lavas will be way more runny and kind of ooze out. But getting back to Io, since Io's observations show us that there's high temperature, low viscosity lava, it's a likely silica pore in composition, so mafic to ultramafic. Remember, mafic is things like basalt, so basaltic to ultramafic, which there isn't a great Earth analog to, because on Earth ultramafic volcanism ended a long time ago, but it used to be called comatite. There's still some ancient comatites, but they're not actively erupting on Earth anymore. And this mafic to ultramafic composition of the lava on Io's surface indicates that the interior, or the mantle, the source for that lava, is relatively poorly differentiated or primitive. We call this primitive because, like we just mentioned, on early Earth, this more ultramafic volcanism was active, and then now it's become more and more felsic. And so this was actually unexpected. But why was it unexpected? Well, magma differentiation via something called partial melting produces increasingly silica-rich or increasingly felsic lava over time. And now I know you're asking, what is partial melting? So let's talk a little bit about partial melting. This is becoming more of an igneous petrology lecture than it is an Io lecture, but I promise we're going to tie it all together at the end with Io information. I just have to set the background first. So partial melting, let's get into it. Well, Earth's volcanism is driven by melting of mantle material, as we can see by this subduction zone over here. We've got an oceanic plate subducting under a continental plate that brings water down into the mantle, where melting then occurs because water lowers the melting temperature of that material, and then that melts, it rises because it's hot. And then this is where partial melting occurs before it erupts on the surface of Earth. And that's because the mantle and where the partial melting is occurring does not reach high enough temperature to melt everything in these magma chambers here. And because magma chambers contain heterogeneous material with different melting temperatures, The material that has the lower melting temperatures will melt and erupt at the surface of Earth, whereas the material with the highest melting temperatures will stay behind because the temperature likely won't get high enough to allow that material to melt. And it turns out that the material with the lower melting point is felsic material, felsic magma, melts and then erupts at Earth's surface, whereas the mafic material, or relatively more mafic material, stays behind because it has a higher melting temperature and the temperature doesn't reach high enough to melt all of the material in the magma chamber. Now, I'm not saying that never happens, but it typically doesn't happen. On early Earth, things weren't fully differentiated yet and temperatures were higher, so that happened more often. But the gist of this slide is basically partial melting always leads to more felsic material erupting than what was in its source. So partial melts are always more felsic than their source. And because on Io, we've observed temperatures in excess of what is necessary to melt very mafic to ultramafic material, that's why we think that ultramafic volcanism could be occurring on Io. But we still aren't sure why or how there's ultramafic lava on Io's surface. Because it's so volcanically active, we would have expected it to be way more differentiated by now, therefore felsic at its surface. But that kind of brings us to formation history, because you might be asking, well, if it formed recently, maybe it's in its early history where it still has ultramafic volcanism, just like Earth had in its early history. But we don't think it formed recently is the issue here. So now we need to talk a little bit about how and when Io and other bodies in our solar system formed. First, allow me to explain briefly how Earth formed, and then I'll get to Io. So the sun and planets, such as Earth and our solar system, formed from the primordial solar nebula. So we had a supernova, a star exploded, there was a bunch of material in a dense cloud, and then you had the sun form at the center of that dense cloud of material. And then what was surrounding the early sun at that time was a bunch more material, rocky material, gas material. And this material accreted into dust particles, then larger aggregates, then even over 1 kilometer sized planetesimals. And then those planetesimals accreted to form larger planets like Earth and other planets around 4.6 billion years ago. And this was pretty rapid. Earth grew to about 63% of its modern mass in about 10 million years, which is really fast on geologic timescales and solar system timescales. And bombardment, impacts, and accretion continued for millions of years after that initial formation of what was Earth at the time, which also contributed heat to Earth along with isotope decay and gravitational compression. And this heat caused Earth to be very hot and therefore pretty melted in its interior, which allowed for differentiation to occur, in which denser materials sank to the core, like iron-rich material, and less dense silicate material rose to the outer layers of Earth. And the primitive crust on Earth was ultramafic before being differentiated by tectonics and volcanic activity, and it over time became increasingly felsic as that activity continued for 4.5 billion years. And Io, on the other hand, was not part of the planets that formed from the solar nebula. Instead, it formed out of a subnebula that was forming around Jupiter as Jupiter formed, because Jupiter is so freaking massive and it has a lot of gravity. And in this subnebula, moons accreted, such as Io, and were heated from compression, impacts, isotopes, just like Earth was heated, but also from tidal stress from Jupiter and the other moons forming around them. So the pull and stretching from the gravitational forces around Io caused it to be very hot. And enough heat was generated to cause melting and differentiation into a core and mantle. And that's how we know that Io, well, likely formed along with the solar system and planet formation a long time ago, over 4 billion years ago, and also was relatively differentiated, at least into a core and a mantle. But we still don't really understand the degree of differentiation in Io's mantle, especially its upper mantle that feeds volcanism at Io's surface, and why that would still be relatively primitive or ultramafic. So here's some of our ideas of what the interior or mantle structure and composition of Io is that might explain the ultramafic volcanism and other volcanic material at Io's surface. One possibility is that ultramafic lava is widespread on Io. We still haven't confirmed that. We haven't even confirmed fully that it's present on Io, but we think it is because of those temperatures. In any case, if we observe widespread ultramafic volcanism on Io, that could either indicate a magma ocean in the upper mantle of Io, as shown down here in this figure, and that could feed poorly differentiated ultramafic volcanism because everything's mixed and melted and therefore not going to differentiate. Or there's deep mantle dissipation and superheating. So there could be a scenario where there's a deeper source for the volcanism at Io's surface, and the magma undergoes superheating, which could lead to a more primitive or ultramafic lava composition at Io's surface. But if the ultramafic volcanism is only localized on Io rather than globally widespread, and there's more widespread mafic volcanism rather than ultramafic, that could indicate a not quite magma ocean, so more of what they call a mush or sponge mantle. So very large magma reservoirs, but they're relatively disconnected or disconnected enough to not be a full ocean. And this sponge mantle scenario is, from what I've read, the more likely possibility than the other thing that could lead to this widespread mafic material scenario, which is recent partial melting. So recent partial melting is just what I mentioned earlier. It could be that Io formed more recently and it's in its early stages of differentiation, and that's why we're observing ultramafic volcanism on Io, just like there was on early Earth. But this seems unlikely based on when we think these moons, these Galilean satellites, formed. So it's kind of just a potential possibility. And the last scenario is also relatively unlikely, which is if ultramafic lava is absent or largely absent on Io and previous observations were just not correct, which is possible. Felsic lava could be present, and if felsic lava is widespread or even just present a little, then it's likely a more differentiated scenario than we think, similar to Earth, where you have partial melting and, you know, a good mix of mafic to felsic material at the surface. But again, our observations of probably ultramafic lava have kind of negated this scenario, even though before observing Io's lava, that's probably what we would have expected to see. But I also can't say with certainty that it's one of these three scenarios, because it's also possible that Io is some weird mixture of these, and we can't yet predict it because we just don't have a full understanding of how tidal heating works, the history of Io's formation, its evolution, both in its interior and exterior. We also don't have sulfur or such large amounts of sulfur volcanism on Earth, and since that's a very large component of Io and Io's volcanism, that could be affecting the processes that lead to silicate volcanism on Io as well. And we also have just very different temperature pressure conditions at Earth's surface and in our atmosphere. We have an atmosphere, first of all. Io has a very thin and tenuous atmosphere, and when volcanism is occurring and blowing off into space with hardly any atmosphere at all, the eruption styles can be very different, which can make it hard for us to determine things based on geology and morphology of Io alone. And so there's just a lot of things we need to study about Io, and some of our still unknown questions about Io and why I think we should have an Io dedicated mission include, what is the composition and structure of Io's mantle, which is kind of the question we've been trying to tackle this whole video. And why is Io still so hot? If it formed so long ago, we don't really understand tidal heating, how it's still so hot and ultramafic and potentially even has a magma ocean, which is like super cool. How is tidal heat dissipated on Io and other tidally heated moons like Europa, Ganymede, Callisto, Enceladus, Titan, all these other moons out there that might have life? how and when Io formed, and how has its volcanism evolved over time, what controls the variability and distribution of volcanism on Io, like eruption style, composition, temperature, and its spatial variability. And for all of these questions, we really should have a dedicated Io mission, which has yet to happen. So NASA, if you're watching this, let's do it. Anyway, if you guys want to learn more about the variability and distribution of volcanism in Io and eruption style and stuff, I'm going to talk about a lot of that stuff in my video about lava lakes on Io, which are really awesome, and I didn't get to touch on here, but I will talk all about in that video, which will pop up here if it's out by now. And you can also check out the first Io video I made a while back, which is kind of general Io information about its volcanic activity and stuff. And that video really sets the stage for this video and other Io videos I will make in the future. And if you guys want to check out other planetary science videos about other moons and planets in our solar system, you can click the playlist, which will pop up here any minute now. And if you guys, oh, there it is, want to check out the reference I'm using to make this and other Io videos, it's called Volcanism on Io by Ashley Davies, and it's a really awesome and helpful book. It's linked in my description below. Thank you so much for watching, and I'll see you guys next time. Bye. Okay, so for those of you who stayed throughout the entire video, you get to see what has been sitting behind me this whole time, which is a blanket that has this weird stuff on it. And what this weird stuff is my best interpretation of Io, I guess. I made this blanket with Io, Jupiter, and a little spacecraft there, and my cat, sorry. And yeah, I just made an Io blanket because I did an internship where we studied Io this summer, and I was inspired, and I used to make blankets like this all the time because I enjoy it. And I thought I'd just have it in the background for this Io video because it's a video about Io. Oh, hair just floated by. Anyway, that's it, and I hope you guys enjoyed, and I see you guys in the next video. Bye.